Good morning. We are getting ready for the final exam. Here's a set of problems that I put together as a review. We did this for all of the midterms, and so I thought it would be good to have a sample of problems leading up to the final exam. Now, a final exam includes so much. You know, there's so many places to review, so many different topics that we've gone through. The primary purpose, I guess, one of the features of this particular review is that you get a chance just to see what a final exam looks like. So here's a set of problems that showed up on a final exam some number of years ago. And so you can see that, as we've talked about, the format for the final is going to be just 8 problems. So they won't have separate parts A, B, C, D. It's just going to be 8 straight questions. Now, some of them could be, more straightforward. Some of them could be a little more involved mathematically. Most of them are probably quite conceptual in nature, in that, the idea here on the problems is to check your understanding of how to set a problem up. And so getting the problems set up correctly, or stopping and thinking about the problems and then getting them set up is going to be important. So, so again, let's go ahead and take a look at this particular set of problems that we've got here. Problem 1, so the problems are set up so that they're kind of uniformly taken from the course, which means that if you think of the course as being broken down into 4 sections. So we had 4 weeks and then a midterm, 4 weeks, midterm, 4 weeks, midterm, 4 weeks, midterm. So if you take a look at each one of those 4 weeks, it covered 4 chapters, a chapter a week, that's all we ask. And so the first 2 problems are taken sort of from the first 4 chapters, and then a couple problems from the next 4 chapters, the next 4, and then the final 4. Now again, it's not possible to cover everything in 8 questions. And so in addition to taking a look at these problems, I think it's useful to take a look at these. These are a good set of problems to go through. I mean, after all, these have actually shown up on a previous year's final exam. But remember, you can look at your midterm problems, look at the practice midterm problems that we did, the actual midterm problems. You've got homework problems, and then the examples that we looked at in class. And so all of those are excellent sources. I realize time is limited, but whatever time you have available for a study and preparation for the physics final, those are the places to go and look for problems in terms of practicing your problem solving skills. So the first problem, actually, I guess I want to say, this might actually officially be from chapter 5. So maybe chapter 5, chapter 4 here. I was going to say problems from chapter 4 more likely. You could have problems from chapter 2 or 3, but 4 is very likely because it can include everything. And so anyway, let's go ahead and start with this. So what we've got is we've got an object that's dropping through water. And so what we've seen with that is, so here's a force diagram. Here is the gravitational force. Here is the resistive force. We said that for a fluid like water, that saying that the resistive force, the fluid resistance, is roughly proportional to velocity turns out to be a fairly good model. And so when we actually carry out these experiments, we do find that water resistance tends to be roughly proportional to velocity. So these resistive forces are complicated, and so we're expecting it's not exactly following this model. But once we have a model like this, it allows us to go in and mathematically make other sorts of predictions about what we might find when an object is moving through a fluid. And so here's the water dropping. There's a gravitational force, there's the fluid resistance force. I've written the acceleration downwards, so I'm assuming that if the object is released from rest, it would pick up speed. Now, initially, it's picking up speed. Initially, it's going to be dropping at the gravitational rate of the gravitational force, and at some point, the fluid resistive force will match the gravitational force. So I'll have v sub t is equal to mg. Now, one thing I do want to point out in this problem is we're ignoring buoyancy. We're assuming that this object is dense enough that the buoyant effect of the water is going to be a small enough effect that we're not going to concern ourselves with it. It is a final exam. It does kind of feel like maybe buoyancy should come into play here, but we're going to ignore buoyant forces for this particular problem. So if we do that, then what we're going to end up with is a terminal velocity. What's going to happen is the speed's going to pick up, it's going to go faster and faster, but then the fluid resistance gets larger, and that means at some point the force due to the fluid resistance is as large as the gravitational force, and at that point the object stops accelerating. The acceleration approaches zero. Now, what they're asking for in the problem is just to go through and show that the acceleration can be written in terms of the velocity according to this formula. So let's try this. Using Newton's second law of motion, the acceleration then would be mg minus bv over m. That's the standard formula, forces divided by mass. Now, what we've shown here is that, what we've done here rather, let's start here. Let's factor out a g. So I'm going to factor out g. I'm going to divide through by m. And so I can bring out a factor of g, and then there's a factor of 1 for this first term. The second term is going to end up with b over m divided by g, because we factored out a g, and then the factor of v. So what I'm trying to do is get this formula to look like the formula they're suggesting. And so I've gotten to this point, and then it says that we can use the terminal velocity. We want to work this into the formula. Terminal velocity should be given by mg divided by b. So if I go back and look at my formula, I can see that mg divided by b is right there. And so we can take that out and replace it with terminal velocity. So it's really just showing that there's mathematically, there is this alternate way we can represent the acceleration in terms of the terminal velocity and the gravitational field. And what it says is that when the velocity is 0, when the object is at rest in the fluid, then this part of the formula drops out and the acceleration starts out to be g. And then as the velocity approaches terminal velocity, the acceleration will be reduced, and at the point where the terminal velocity, at the point where the velocity reaches terminal velocity, well, this becomes vt over vt, that goes to 0, and the acceleration goes to 0. So we can express the acceleration in terms of the terminal velocity. Now, what would happen if we threw something faster than terminal velocity? What if the v were larger? Will the formula still work? And it looks like it does, because if v is larger than terminal velocity, this would become a negative value, and it would say the acceleration is back in the opposite direction. So yeah, this formula actually works independent of, well, it works for the cases where v is 0, it works for the cases where v is less than terminal velocity, and it also works for v greater than terminal velocity. All right, let's move on and take a look at this second problem. So here we have a couple blocks, and we've got a diagram on this one, a couple blocks in contact with each other. It says we do have kinetic friction, so, I have to say on this exam, we kind of bypassed problems that were exclusively chapters 2, 3, and 4, and went right ahead to a couple of problems from chapter 5, which included much of the, many of the ideas presented in chapters 2, 3, and 4. Okay. But we do have friction here, so it's at, the kinetic friction's at 0.12, the coefficient. The blocks are being pushed by a force of 60 newtons. We're supposed to find out how much force is there acting between the two blocks. Now to do that, I need to think of the blocks as being independent. I need to write down some diagrams. So we'll get some diagrams set up with the normal forces are in there. We've got the gravitational forces, M1G, M2G, the frictional force F1, frictional force F2. So that looks like the force diagram. It looks like we have everything listed. Now remember, you know, the normal force acting between the two blocks, that's just one value. So I don't have to solve for two items here. Whatever the normal force is pushing back on block 1, that's going to match whatever the force is pushing forward on block 2. And so, so I wrote down the given values. Here's the kinetic coefficient of friction. Here are the masses of the two blocks. And here is the force acting on them. Now, what we could do here, there's a couple different approaches that we've looked at in these kind of problems. I decided to take this approach. I decided to say, look, the acceleration of block 1 is the same as the acceleration of block 2. We're just going to call that A. And A for block 1, if I think in terms of separating the two blocks, if I write down a formula for block 1, that acceleration is going to be related to the force in the forward direction minus the normal force minus the frictional force. So I'm going to have big F minus N minus F1 over M1. Now that's for block 1. Now block 2 has the very same acceleration. Its acceleration formula is going to say the acceleration is related to the force divided by M2, where the forces here are N in the forward direction and F2 in the backwards direction. So what I'm trying to do here is I'm trying to bypass solving for acceleration. They never ask us to solve for acceleration. I can write this equation down relating the accelerations from the two sides in terms of forces and masses, and then I can cross multiply. I can bring the M2 over to here and the M1 over to here, and then I've got an equation, M2 F minus N minus F1 equals M1 N minus F2. And what we can do now is we can actually show that these two terms that we have, I took the n's, we're solving for n, so I took the n's and I put those on the same side. Now I guess that means this side over here. So I'm going to bring this n over to here, but then I'm going to represent it on the left side of the equation below. I'm bringing all the n's over to the same side, and then what will be left is m2 times f. But then I've got this m1 f2 minus m2 f1, which is kind of interesting. Now, the frictional forces, we can rewrite those in terms of the coefficient of kinetic friction. So as I hope you know, in a problem, they could ask directly about the frictional force, or it could be written in terms of a coefficient of friction. And in this problem, we have a coefficient of friction. So let's go ahead and use it. It says that the friction for block 1 should be given by mu sub k times n1. n1 will have the same magnitude as m1g. So I can make that substitution. I can say mu sub k times n1, where n1 will equal m1 times g. That gives us friction force number 1. Here's friction force number 2. It looks the very same. But this one's in terms of N2, and N2 is going to equal M2G. So those are my frictional forces. Now, is the coefficient the same for both blocks? And it turns out it is. So maybe they're made out of the same material, they're sliding along the same surface, And it's also possible that they're different materials, but they happen to have the same coefficient. But since they do have the same coefficient, mu sub k, when I multiply this by m2, and I multiply this one by m1, as we see in our formulas here to the left, those terms are going to cancel out. And so it says that if the coefficient of friction is the same for each of these objects, then the normal force can actually be written in terms of, independent of the frictional forces. The normal force between the two blocks will be m2 over m1 plus m2 times F. So kind of interesting, you would think, well, doesn't the frictional force have an effect? But because proportionally the frictional force from block 2 and block 1 are the same, it doesn't actually affect the n values in between. Now it does reduce the acceleration. The acceleration will be less as a result of those two frictional forces, but it doesn't affect the normal force acting between the two blocks. Now, I put all the numbers in, and let's see, this was 60 newtons pushing the whole system combined, so 60 newtons for both blocks in some sense, but the normal force between here then is proportionally enough to create the same acceleration in the 6 kilogram block as in the 8 kilogram block. So it's 6 kilograms out of a total of 14 kilograms multiplied by the 60 newtons gives us 25.7. So a couple questions we could ask, which good conceptual questions here. What would happen to, let's say, the acceleration if we were to reverse the blocks? What if I took the 8 and 6 kilogram blocks and I switched them? And you're thinking, well, that's not going to change the acceleration. It's the same amount of mass. The frictional forces will be the same. They'll be placed at different locations, but we'd have the same friction. We'd have the same force pushing them. Yeah, the 6 and the 8 reversing, that shouldn't change anything. What would happen to the normal force between the two blocks? What happens between the two blocks if we switch their placement? And that would make a difference. So if I had the 8 kilogram here and the 6 kilogram here, the normal force between them would need to be larger. It would need to, well, you can see how the formula would change, right? This would become m1 divided by m1 plus m2. That would be 8/14 instead of 6/14, and it would be more newtons. So it would be 30, is that right? 34.3 newtons maybe. You can check that and see. So you can ask yourself what happens if the blocks get switched in their placement. Okay. So as always, kind of interesting to think a little bit beyond what the immediate question is asking. But this is a good problem. This is an excellent problem, I'm going to say, in terms of thinking, going back and reviewing, thinking about force diagrams, and thinking about forces acting between objects. If you've got a series of objects lined up, this has friction in it, which is nice. What would happen if the coefficients of friction were different? What if, I had a mu sub 1 and a mu sub 2 that were different? Well, these guys would have to stay in then. So those two terms, then I would have to evaluate and include that in the calculations. All right. All right. So I'm going to say that's a really good problem. Problem 3, we have a Ferris wheel. There's not a diagram here. There's a Ferris wheel. It's got a radius of 20 meters. So 20 meters. Yeah, that sounds pretty fun. So 40 meters up. That's really high, right? That's like a 10-story building or something. So it's a good sized Ferris wheel. Now, it's making a revolution every 15 seconds. So 1, 2. So it's moving around at a pretty good speed. And it says we've got a passenger on one of the seats, 60 kilogram passenger. What force will the passenger exert on the seat at that point? So here's the Ferris wheel diagram. Now this is This is circular motion. So the person is going around in a circle, and what was the radius? Ooh, I didn't write it separately. The radius is 20 meters. The period is 15 seconds. It would have been good to write those separately. In any case, what we're doing is we're looking just at one location. We're looking at a location right at the top. Now, when the passenger, see that little block with the little m? That's our passenger. So the passenger here, little m, is sitting on a seat, and what we want to find out is, what's the contact force? What's the normal force acting between the passenger and the seat? When we say what's the force of the passenger on the seat or the seat on the passenger, that's what we're referring to. Now, since the person is in circular motion, they do have an acceleration, and the acceleration will be towards the center. Now, that's a kinematic statement. We have not said anything about gravity yet. Gravity in this problem does not come in as an acceleration. It comes in as a force. So this person is not in free fall. Sort of. So there's an acceleration taking place, and there's an acceleration towards the center of the circular motion. These are the forces we have to work with to generate this acceleration. Now, gravity is going to come in as a force. It's going to come in as mg. So this acceleration can be set equal to mg minus n over m. So I'm going to say this. I'm going to say practice. Make sure you are practicing writing these acceleration and force formulas down, not from your notes, where you're just trying to write a series of notes, because you get a problem like this, and maybe the diagram's a little different from what we've seen before. So in any case, stop and think, yeah, here are the forces, here's the acceleration, this is what the formula needs to be, this is going to be how I solve for that normal force. So again, conceptual, right? Understanding what the normal force, understanding that the normal force is what we're talking about in the problem. So the normal force is the force we're talking about, and then setting up the force diagram, solving the equations, so we have a formula to tell us what that normal force will be. Now, we've been told the passenger is 60 kilograms. We know the Earth's gravitational field. We're assuming it's Earth. And so the only thing really left to go through and solve for now is we still need to solve for the acceleration. Now, the acceleration for circular motion, we've written that as v squared over r. We've written it as r times omega squared. So we've kind of written it three different ways. This was one that we started using, maybe this was in the gravitation chapter, but it certainly applies generally, that the acceleration for circular motion is given by 4 pi squared, the radius divided by the period of that circular motion squared. And so plugging all the numbers in, it says that this passenger, as they go around this Ferris wheel, there is a 3.51 meter per second squared acceleration taking place at all times towards the center. And so if you're right at the top, pointing towards the center is downwards, and that's how we set up our force diagrams. What would happen, what would change if the passenger were here on at one of the sides, or what would be different if the passenger were at the bottom, right? I mean, you guys have ridden Ferris wheels. You know, at the bottom you feel heavier, and at the top you feel lighter. So you could go through and calculate the normal forces and see how different they might be. This problem is just asking about the top. So this is the acceleration we have to work with. We plug that in. We get a force. Now the force, this is what they're asking for, 434 newtons. Now how does that compare with if the Ferris wheel were not moving, if there were no acceleration taking place? So if there were no acceleration taking place, then we would not be subtracting off this acceleration, and we'd just be using the gravitational field. 60 times 9.8, that's going to be closer to 600 newtons rather than 434. Now, another way we could get an idea of how much of a reduction in normal force are we expecting. We could take this force and divide it through by g to get an effective mass. Now this is not really the mass of the person. The person continues to be 60 kilograms. That's what we've plugged into our force equations. But it's going to feel like, person's going to feel like they're only 44.3 kilograms. In terms of how heavy do they feel like they're being, you're sitting down on a chair and you can feel that contact force. The contact force between the passenger and the chair is as if the person were 44.3 kilograms. They don't feel as firmly attached to the chair as they would be if the Ferris wheel were not in motion. So that's what we're after here. Okay, so this is good. This includes some circular motion stuff. Not really the gravitation chapter so much, but we did get some circular motion and circular motion kinematics and circular motion dynamics in terms of forces. All right, let's take a look at problem 4. This looks like we're going to depend here on some momentum conservation. Back in chapter 9, this is asking about water being, fired, water shot at a wall, and then the water hits and it runs down the wall. What that creates is it creates a force, a set of third law forces. The water is exerting a force on the wall. The wall is exerting a force back on the water. The effect of the wall exerting a force on the water is it slows it down. The water comes in at a certain speed and then it hits. Now in this case, it says that it just goes to 0. In other cases, it could be that the water reverses directions and bounces off. Now if it bounces off, that's an even bigger force required for that to happen. But in this one, it's just enough force to stop the water, and then the water runs down the wall. So back in chapter 9, we had worked with calculating forces in terms of the rate at which momentum is being transferred. In this case, we can think of it as the force of the wall and the water. It's the rate at which momentum is being removed from the water. The water comes in with a bunch of momentum and the wall takes it away. Now, since these two forces, the force of the water on the wall and the force of the wall on the water, they're the same magnitude, well, that means I can solve either way. I can think of what's happening in terms of the water, or I can think of what's happening in terms of the wall. Now, the wall would be hard to think in terms of because the wall is anchored into the entire planet, and the planet's not going to recoil much from this force, but the water does. So we can focus in on the water and say, the water's coming in at a certain rate. There is a certain amount of mass during a certain time interval. I'm going to call that dm dt. Now, the momentum in the numerator includes not just the amount of mass, but how is its velocity affected. So the velocity coming in with the water was v, but at the end, once it had hit, the velocity was 0. So there's a difference of velocities are keeping track of the difference in momentum for each little piece of mass coming through. And they gave us a dm dt. It was given as 0.475 kilograms per second. So we've got that part, and then the difference of velocities was 20 meters per second. Now I kind of dropped, I guess I did drop the minus signs here. I wrote this as absolute value of the force. I'm just going to take the speed of the water and times dm dt. That's what this formula simplifies to. And I thought, I'm not going to worry about the minus sign because I know that the force acting on the water is in what we're designating as a negative direction. It's opposite the direction of the velocity. But at the end of the day, we just want to find out how much force there is. the diagram that we drew is already letting people know that the force will be, there'll be two forces, one acting on the water, one acting on the wall, and they're going to be the same magnitude. All right, so, and then this worked out to be 9.50 newtons. Another thing to keep in mind with these problems is if you get stuck, if you get an answer but it doesn't seem to make sense, it's like crazy too big or crazy too small, write a quick note and let me know what you're thinking. So now you want to, you don't want to spend too much time writing notes on your exam, but if you do get stuck, write something down. If you think something's too large but you can't find the error, write down what you're thinking. I think this is like 1,000,000 times too big, but I can't. And that can make a real difference. Because then I realize that you kind of understand that the numbers you're getting don't make sense, but that you're kind of stuck. You can't find your error right at that time. So that can make a difference. All right, moving on to problem 5. So now this looks like the gravitational chapter here. It says the mass of the Earth is 81 times the mass of the moon. The distance between the centers of the Earth and the moon is 384,000 kilometers. At what location in space would there be a net gravitational force on an object from the Earth and the moon that would add up to be 0? Now, you can't really isolate the Earth and the moon because there's going to be a gravitational effect from the sun, which could be significant in these calculations, and maybe even dominate. The forces from the other planets are there too, but that's probably not as large as from the sun. In any case, what we're doing in the problem is we're just isolating Earth, moon. Now, they asked about gravitational force. Now, gravitational force will be 0 if the gravitational fields cancel out. So for example here, let's say we have an object placed at some location. It's got a mass of little m. Well, I don't have to know what the little m is equal to. I could, by setting the forces equal to each other, the little m's will cancel out anyway. So I can work in terms of the gravitational fields. Now, the only way, gravitational fields are vectors. So the only location where we can get the gravitational fields to cancel out would be a point where I can get those two vectors to point exactly in opposite directions. It's only going to be where those vectors point exactly opposite to each other. And so that's what I've drawn here. It's got to be a point along the line connecting the center of the Earth and the center of the moon. All right, so that's significant, saying that that's where the location would be. And then what we want to do is we want to get the magnitudes to match. Now, I'm calling this distance from the center of the Earth out to this location. I'm calling that distance from the Earth. And then here, from the center of the moon to that location, I'm calling that the distance to the moon. Now, the total distance d, which is the sum of those two numbers, that's 380,000 kilometers. So I'm setting the gravitational fields equal to each other, and here we go. I'm writing down the formulas for the magnitudes of those gravitational fields, canceling out the g's, and then I'm taking the ratio route. You can kind of, when you're reading this problem, it says the mass of the Earth is 81 times the mass of the moon. That's kind of ratio information. So I know how the masses compare. Now, what we're trying to do is figure out how the distances from the diagram, DE and DM, compare. And it turns out from the formula here, we can show that the ratio of the squares of those distances have to equal the ratios of the masses, and that's given as 81. Now, 81 just happens to be a perfect square, so it's saying that the distance on the diagram, DE, is going to equal 9 times DM. Now, we expected that. We expected that because the Earth has a lot more mass than the moon, that the point that we're looking at would be much farther from the Earth, right? The crossover point, if you go back and watch those Apollo moon missions, you know, where they talk about now we're past the crossover point. So at the crossover point, now it's the moon's gravitational field is now speeding them up. All the way from Earth out to that point, they were slowing down. But once they cross that point, they start to pick up speed as they approach the moon. Let's see, the algebra on this. So the dE can be, where did we write this? dE plus dm is equal to the total distance. Now the dE I wrote as 9 dm's. So that says that 10 dm's equals d. So dm needs to be 1/10 of the distance and dE needs to be 9/10 of the total distance. So that separates out almost too cleanly, right? And the factor of 81 is, it's a bit of an estimate, but it does turn out that this point is 9/10 of the way to the moon in terms of center to center distance, and so that's what's here. So the distance from the moon would be 1/10 of that number. This would be 9/10. Now the moon, Earth's moon it's not small, especially in size of its relative size of the parent planet, I guess. If you look across our solar system, there's what? There's like 7 large moons, I think. Jupiter has 4 large moons. A couple are larger than our moon. I think a couple are smaller. Saturn has 1 large moon. Neptune has a large moon. And those are all big planets, right? And then Earth has a large moon. So if you look at the inner solar system, Mars doesn't have any moons anywhere close to the size of, and Venus doesn't have any moons at all, or Mercury. So the Earth-Moon system is a bit of an anomaly. It's kind of interesting that this double, what's considered often a double planetary system got set up, formed within the solar system. So, and that's, gravitationally, that's actually a bit tricky. I think the most common model that planetary scientists think in terms of right now is 2 large planets, one the size of Earth and maybe one the size of Mars roughly, at some point collided, and the remaining material, the Earth's moon is made of less dense material than Earth, so they didn't form from kind of the uniform mixture of what was in this part of the solar system. So there are different ideas as to about how that could have happened, how Earth's moon formed from material not low density but less density than Earth in general. So kind of an interesting double planetary system that we have here. All right, these are the numbers that we ended up with. Moving on to problem 6. This looks like something coming out of maybe chapter 12, right? Oh my gosh, where's the rotational motion? Okay, warning, there is nothing on rotational motion from this set of problems. Make sure you're looking at rotational motion. It's gonna show up on the final. It's got to be there. I'm not sure how we ended up with a final that didn't have any rotational motion on it. So here we are in chapter 12. And so what we've got is we've got a beam and a cable and then a sign hanging down. So there's the gravitation acting on the beam. There's the gravitational force acting on the sign. Now it says in this problem, when we did all these problems in chapter 12, we said that typically we think of a hinge placed at this location. A hinge so this can freely swing back and forth so we can reliably evaluate the torques that are coming from the cable. But what it says in this problem is that, this shows a little bit of a gap, but what it says is that, this came loose. So there's actually nothing holding that beam in place except friction. So there's just a frictional force holding it in place right now. Or maybe the designers planned it this way. Oh, let's build something where we don't actually use bolts to hold something together. Let's just let friction do this. So there's going to be a frictional force here. Now what they're asking is, how large would the static coefficient of friction need to be in order for that beam to stay in place? Because if there's enough friction, maybe this works. I wouldn't design a building this way or a sign this way. But let's take a look and see what we've got going on here. So here's the beam. We talked about the two gravitational forces. There's a tension in the cable. Always pay attention to the angles. Make sure you're getting the cosine and sine components correctly placed. So it looks like T cosine is going to be the horizontal component and T sine is going to be the vertical component. Now at this side, instead of saying Fx and Fy, Fx is the normal force. So these things are in contact, but there's no hinge holding it in place. The wall is pushing the beam outwards. And then there's a frictional force, and we're going to need that frictional force to be in the upwards direction. So if we look in the vertical direction, here's my vertical direction formula, upward forces match downward forces. That would be T sine theta plus that frictional force along the wall are offsetting the two gravitational forces. So far, so good, right? And then, in the horizontal direction, the n needs to be equal to T cosine theta. Here are the two masses. They're at 10 and 80 kilograms. Now, that's about as much as we can do with the forces themselves, and we just don't have enough information from those to be able to solve for the tension or to solve for the normal force. So what we're going to have to do, we're going to have to look at torques. And so I thought, point A has worked for us in the past where point A is the hinge location. This time I went with point A. I said let's add the torques together around point A. And let's see, theta is equal to 40. That's just given information. Let's see, what torques do we have? If I look at point A, I can see that T cosine theta drops out. Frictional force drops out. Normal force drops out. Those all drop out of the torque equation. They're not going to have torques. They don't have a lever distance. T sine theta does have a lever distance. And relative to point A, T sine theta has a lever distance. I'm just going to call it L. Did they tell us what the length is? That's 1 meter. I'm going to call this distance L. Now, mg is in the opposite direction in terms of torques. T sine theta is tending to create a positive torque. Mg and big mg are creating negative torques. So the little mg is at a lever distance of 1/2 L, and big mg is at a lever distance. Now this one was a little tricky, not bad though, at 3/4. So what we're assuming is that the sine being held up here is, the center of mass is right at the center. So that would place it at 75 centimeters or 3/4 L. So the way I set it up, all the L's cancel, and I'm just working in terms of those fractions. So it says that T, the tension in the cable, is given by mg times 1/2, big mg times 3/4 divided by the sine of the angle. And then there's a, what is that? Is that the sine? Okay. Something else is in there written. The tension worked out to be 991 newtons. And so once we get the tension determined, then we can come back and solve these equations. I know this is 991 and this is 991. That allows us to come back. I can solve for friction and I can solve for normal force. So getting the tension, it worked well. We were able to get that tension solved. Let's see, what would have happened if we had done torques over here? That would have given us friction, but it would not have given us normal, it would not have given us T. So I think getting the tension was necessary. I guess we could have solved, yeah, that would have worked too. We could have done torques around here to get friction, once we get friction, we could have solved for T. So yeah, either place would have worked in terms of torques. So what we've got now is we've got the frictional force calculated, 245 newtons. The normal force coming from here, 759 newtons. So it's saying that the coefficient of static friction would need to be at least as large as that ratio. So it needs to be as large as 0.323. And that shouldn't be too hard, right? Now again, I wouldn't build a sign like this, because if a wind comes up, if the normal force is reduced, someone comes along, hits the sign, it's just going to fall down, right? This part of it's just going to rotate down, but hey, this would be a way to go in and use friction for that. All right, a couple more examples here. It looks like we've got something oscillatory, something kind of chapter 14-like, and then something that looks kind of like chapters 15 and 16. So let's do those. So on problem 7, it says that we've got a 30-kilogram child jumping from a height of 2.7 meters onto a trampoline. The trampoline depresses a maximum of 30 centimeters. So when I looked at these numbers on this problem, I thought, wow, this is 2.7 meters. Let's see. Yeah, 2.7 meters. And so 2.7 meters, that's getting up there. It's like, 9 or 10, 9 feet. So this kid's like jumping off the house onto this trampoline. And so that's quite a ways. Now, it's like they jump off the house onto the trampoline, but the trampoline only goes down by 30 centimeters. So I think the kid's in trouble. I don't think that's enough give in the trampoline. Now, it doesn't ask us to go in and solve for the forces or the accelerations, but I'd be curious to figure what the acceleration might be. And if it's an ideal trampoline, which is kind of what we've looked at with these ideal springs, then the kid could jump off the house onto the trampoline and then bounce right back to the top of the house, right? Which would be really cool if you could do that. So anyway, here's this kid dropping off of the house onto a trampoline, and it depresses the trampoline by 30 centimeters. The height the kid jumped from was 270. Now, they want to know what is the what did they want to know? Oh, they want to know what the period of oscillations will be. Now, what it says here is, assume that the trampoline is an ideal spring, not a good idea. And then it said, what would be the period of small amplitude oscillations with the child, where the child is just in contact. So this is just a test run. Basically what the child is doing here is figuring out what the K value is going to be for this trampoline. So they jump off the house, depresses it by 30 centimeters, and then they set up formulas for using energy conservation. So what they're going to say is, from the initial starting point to the final starting point, the child has dropped a distance of h plus x. So that would give a potential energy of mg h plus x. So mg h plus x, and then in this picture, what they have is a potential energy in the spring 1/2 k x squared. So that's my statement of energy conservation for the drop. Now that equation can be solved for k. So everything else is known. We know the height, we know the compression distance. Everything went into this formula right here. I hope everything went in correctly. And it ended up saying that the trampoline has a stiffness constant of 19,600 newtons per meter. Okay. Again, it feels like a pretty stiff trampoline to me. If the kid jumped from off the house and it only depressed 30 centimeters. Anyway, 19,600 newtons per meter. I think they need to release the tension on that trampoline. What we can do now is we can go, okay, if this trampoline were used as a spring to oscillate the kid back and forth. So for this, it's small amplitude oscillations, and the kid is climbed onto the trampoline and is just kind of bouncing, not even really bouncing, but just staying attached to the trampoline and letting the trampoline oscillate them back and forth. So if that's the case, then what we can do is say, well, we figured out what the K value was. Now if this kid who was 30 kilograms climbs back onto the trampoline and just kind of oscillates at small amplitude, the frequency of those should be given by 25.6 radians per second. That would say that the cycles frequency, 4.07 cycles per second. So let's think about this too. So the numbers again are a little funny, but these are the numbers that were given in the problem. This is a pretty stiff trampoline, and as a result, the kid is oscillating 4 times a second. So it's like, the kid's on the trampoline oscillating like this. I think trampolines oscillate more like this, right? Maybe 1 hertz, but 4 hertz would be, that's a lot of oscillation going on. The period of the oscillations come out at 0.246, and so I put really with a question mark. So I'm wondering what happened on this problem if somebody just didn't check the numbers going in. Anyway, see what you think. I mean, maybe I made some errors here. If you catch some mistakes somewhere, let me know, because it. Again, what I'm suspect of is that the fact that the trampoline only compressed 30 centimeters. I would have expected it compress a lot if the kid jumped from that high. And maybe the 2.7 meters is extreme. Maybe that was unintended. People weren't thinking about that when they wrote the problem. All right, what about problem 8? So a uniform narrow tube, 3.06 meters long. So that's a good long tube, right? This tube goes on and on. It's bigger than this. It's open at both ends, and it sounds like it's being used as kind of a an experiment or a lab. We actually had a lab like this in 4A, and we've used it kind of intermittently, where we have these long glass tubes. And what you can do is you can hit tuning forks next to them. Actually, they're vertical tubes, and you can fill them with water to close off one end and change the length. And what you do is you listen for resonances. Now, what happened on this tube is it was discovered that when people went in and listened, maybe they had tuning forks at different frequencies or some kind of a frequency generator where they could run through all the frequencies and listen to find out when you hit that frequency, when you hit a resonant frequency, the tube will amplify the sound. So they ran through all these frequencies, and they found out they did get this amplification happening at 275 and at 330 hertz over the range of frequencies that they tried. Now, what that tells us then is these were 2 successive harmonics. Now, the difference between these 2 frequencies is 55 hertz. So this wouldn't be the fundamental frequency, because this would not be the second harmonic. So if that's the first harmonic, it doesn't make sense. So these both must be higher order harmonics already, and we're unsure as to what the fundamental is. So let's find the fundamental frequency. Now, the way we can do that, let's see. First of all, we said the tube is 3.06 meters in length, and so the wavelength of the first harmonic would be, oh, that's got to get changed. That's 2 times this. So this needs to be 6.12, and that, oh, it does. And so I went back, I had some numbers in here, I changed them a bit. So I went back and rewrote it. This needs to get doubled, and that number needs to get doubled. And then I think we're okay. Because if that's 6 times, yeah, I think that's it. So this needs to be 6.12, and this needs to be 6.12. Those I'll make sure to get changed. So here is the standing wave pattern of compressions set up in this resonance tube is what I'm going to call it. And so here we have an open, it's an open tube, right? Yeah. So it's open and open. And you know, maybe we do have some tuning forks or a sound generator, and we're finding resonance at these two frequencies. Now, if those are successive frequencies, then we can use this formula that says that the nth harmonic will be n times the fundamental to show that if the frequency of the n plus 1th harmonic is equal to n plus 1 times the fundamental, then if I take the difference between any two successive frequencies is going to be the fundamental frequency. So I can take the difference between it, and I'm going to guess that is actually the fundamental frequency. Maybe the frequency generator didn't go that low and pick that up. But now what we have to show is, well, if that's true, then the two harmonics we're looking at, the 275 and the 330, those need to be multiples. And it turns out they are. So we quickly check the frequencies here, and we go, yeah, this must be the fundamental because this is the 5th harmonic and this is the 6th harmonic. And yeah, you get these standing waves with multiple compressions inside, and it totally works. You totally hear these, hear this amplification at these resonant frequencies. Okay, so let's get back here though, and so this is going to be 6.12 right here. To get the wave speed inside the tube, we can take a frequency times the wavelength as long as those are representing the same harmonic. And now that we've got the first frequency figured out, we can match that up with the first wavelength, if I get it corrected. So this becomes 55 cycles per second, and the wavelength of the first harmonic is 6.12 meters, and the 6 times the 55, whatever, is going to come in at 337 meters per second. So that's the wave speed. Now what we're using this for is to measure the speed of sound. And so again, in the labs that we've done in Physics 4A, when we're using these resonance tubes, that's what we're calling the lab. It's the speed of sound lab. How can we measure the speed of sound using these resonance tubes? So anyway, this worked out to be 337 meters per second, and we were able to use that as our measurement for the speed of sound for that particular setup. Okay, so again, plenty of stuff to go through in preparation for the final exam. I've got a bunch of office hours set up. Stop by with whatever questions you've got. If we need to, we can open up more office hours. Any questions at all, let me know. I'll have to get the there was maybe just this item. Let me get the keys updated so that they're reading correctly. And any questions, just stop by.